It's very easy to prove, but the proof requires the introduction of a new concept, okay? So let, delta x of t, be a small and arbitrary change of the path x of t. Now, x of t is not necessarily the physical path, it's some path. But x of t is small and arbitrary, but it is subject to the constraint. It is subject to the boundary conditions that delta x of t is 0 when t is t0 and t is tf. That is, this picture, if I go back, all the paths at the beginning and the end points coincide. So we are not varying the end points. We're just varying points in between, okay? So now if I make this change to my path, which is, say, let me just put, so if I take some path and then change it arbitrarily to xt plus delta of xt, where delta just means small, then since the Lagrangian is a function of x and x dot, then there would be a corresponding small change in the Lagrangian, which is of the form of delta L by delta x, small change in x. So this is the partial derivative, okay? And then this would be delta L by delta x dot, small change in x dot, okay? So because L is a function of x and x dot, although I'm using the notation, delta of L, this is nothing but d of L, right? But now we define the variation of the action S. So this is called the variation of the action S as the integral from t0 to tf of delta L. Okay, so this is the definition of the variation of the action. And what is that explicitly? It's going to be t0 tf delta L by delta x delta del x plus partial derivative of L with respect to x dot delta of x dot. The whole thing integrated with respect to t, okay? So this is what the variation of the action looks like explicitly. Before I move on, let me make a few comments on this variation. Now, L is a function of x and x dot, and that's why when we did the change in the path, we had the change in L, or the variation in L, was expressed in terms of partial derivatives. Now, is S a function of x and x dot? What do you think?
Sir, I didn't get your question.
do you think S is a function of x and x dot?
Yes, it is.
Okay. So it's actually what is known as a function now. Okay. So what do I mean by that? So the thing that you are choosing in S, so let me rewrite the expression of x, S. It's t from t0 to t of f, and here it's L of x dot of dt. Now, the form of L is fixed, right? It's the kinetic energy minus the potential energy. And for a given system, we know what the form of the kinetic energy is, what the form of the potential energy is, right? But if I choose different paths, x and therefore x dot, I get a different number S, right? Do you agree, Naheem?
Yes, sir.
Therefore, S is a map from the space of the paths. So it's a map from the space of functions of t, okay, into the real number r. Do you agree with that?
Yes.
So what I'm saying is that S is a gadget. So it has a space in which you can insert an object. And the object that you insert is a whole function called x. Okay, so S is the gadget that you insert is a whole function. Because you're integrating over t here, right? So it does not depend on t anymore.
Sir, I had the question on like how S maps from a path to the real number. Like I give the path and plug it into it. Like since S is a functional, like on the right hand side, don't you have another function as well instead of a real number?
No, I mean, so there are many paths and you choose one of the paths, x. So let's call it x1. And then you plug it into your Lagrangian. So this thing is then fixed, right? Some function of t. And then you do the integral over t, and you have a number, which is a real number. Thus, you see that,
Yeah.
depending on the choice of the function, you get a real number. So usually a function is a map from a real number to a real number, right?
Yes.
But here the S is a map from the space of functions, one type of functions, to the real number. Okay? So that's why this is not a function. This is called a functional. Okay? So this is a new kind of object. Well, it is something you've seen before, but it's a new way of looking at it. It's an integral of a function, but it's called a functional. So sometimes you will see in some textbooks which will say, oh, a functional is a function of a function. That is completely untrue. A function of a function is another function. Okay? Because if I have two functions, f and g, if I compose them, I just get another function, h, right? But a functional is not a function. All right, so such a map is called a functional, and a variation of a functional is what we are defining here. This equation, this defines the variation of a functional, okay? And this is a new kind of variation. And it is this variation that we are going to say is 0 for the specific, if we choose the path, which is the physical path, okay? Okay, So we need one more piece of information, and that information is, if I take delta x square x dot, which is, say, the variation of dx, and you can like argue and you can show it quite it's not very hard to see that this thing is the same as the derivative of the variation. Okay. In other words, the variation of x dot is equal to the variation of x dotted. The two operations commute. And using this, now we can write delta of s, which, let me remind you what it was. It was t0 going to t of f, partial derivative of L with respect to x, delta of x, plus partial derivative of L with respect to x dot, delta of x dot, and then d of t. Now, what we can do is that we can write this as t0, tf, and del L, del x. And then the second one, we can write this as d by dt of del x dt. And then what we do is that in this term, we do an integration by parts. So I'm going to write that term first. So we're going to have t0 tf, and this term is going to become d by dt of del L by del x dot times delta x, and then minus d by dt del L by del x dot times delta x. And then we're going to write this term, which is going to be plus delta L delta x del x. And then the whole thing integrated with respect to dt. Okay? So this is just integration by parts, because if I expand this term, I get two terms. One will cancel this term. The surviving term will give me this term. Now, this is a total derivative term, so we can write it as a boundary term. And if I write it as a boundary term, this is going to be delta L by delta x dot del of x. And the boundary conditions are and t0 and t of f. But we know that del x, whatever our path is, vanishes at these boundary points. So the contribution from this term is going to be 0. And then we have a minus sign from this guy. And then we have an integral from t0 to t of f. And we have d by d of t del L by del x dot. And then we have this term, which is minus, so I'm going to put this in a bracket, minus del L by del x. And then I'm going to factor out delta x dt. Okay? And the principle of least action says that if I choose x to be the physical path, then this quantity, which is delta s, this must be 0. That is what the principle of least action is saying. So if I look at this expression, we see that this guy is small but arbitrary. So for this integral to be 0 means that the integrand must be 0 identically. In other words, it means that whatever is in the square bracket must be 0 identically for the physical path. So the physical path must satisfy this differential equation. And this equation is called the Euler-Lagrange equation. Because the Lagrangian was first order in time derivative, and here we see an extra time derivative, we see that the Euler-Lagrange equation is second order in time. Okay. And now let's just verify that this gives me Newton's law for the simple particle, for which the Lagrangian is the kinetic energy mx dot squared, half mx dot squared minus the potential energy, right? Because then I get that dl by dx dot is mx dot. And therefore, if I take the d dt of del L by del x dot, I get mx double dot. And the other term is going to be del L by del x. Of course, that's just going to give me minus del V by del x. So if I put them together, I just get mx double dot is minus the gradient of x, okay, which is Newton's law. All right, so